Hello students, welcome to this series of classes where I'm going to prepare you for your board exams. What we are going to do is we are going to tackle each chapter one by one, and we are going to quickly revise all the formulae, all the concepts there, and look at what questions the board has asked in the previous years. And once we have that information, we are going to try to solve those questions also. So that's on our agenda. And this is the first session in this series, and we are starting off with the first chapter, which is real numbers. Let's get started. Uh, Quick revision of what we studied in class 9. What are rational numbers? So we know that rational numbers are part of real numbers. Real numbers are divided into two major groups, rational and irrational. We'll come to irrational numbers also. But before that, let's quickly revise what we studied in class 9. Okay, so we were saying uh, rational numbers are numbers that can be written in the form a upon b. And what is special about a and b? What are the conditions on a and b? Can you tell me? So the first condition is that a and b are integers and b cannot be equal to 0. So if b is equal to 0, then this number, whatever you write, is undefined. Think of a number like 35 upon 0. Can you divide anything by 0? We can't do that. It's undefined. We don't know what it's going to be. This process is not defined. Division by 0 is not defined in mathematics. So that's one condition. The condition on the denominator b is that it shouldn't be 0. And on both a and b, the condition is that they have to be integers. Okay, with this quick recap, in class 9 we also studied about uh, decimal representation of numbers. Rational numbers as well as irrational numbers can be represented using decimals. Let's quickly recap that. So, if I give you a decimal number and it terminates, what do we mean by terminating decimal? It's something like 3.5612. That's it, okay, this much. So, it terminates at some point. If I give you a number like this, we can see that it is terminating. As soon as you see a terminating decimal, you can claim that this must be a rational number. How? Because this number can be written as 35612 upon 1, 1, 2, 3, 4. Four zeros, right? So we can see it can be written in the form a upon b, so it's a rational number. All right. What if you encounter a decimal which is non-terminating? That means it keeps on going. There are two such types of decimals. Decimals that keep on going. So one kind is when you have repeating digits, something like, let's look at this number. So 2.131313, and it keeps on going like that. This is one kind of non-terminating decimal. The other kind of non-terminating decimal is where you can't really find a pattern anywhere. Something like 4.3216119 dot dot dot. Okay, we don't know what number is going to come next. We can't find a pattern. Whenever you find a recurring or a repeating decimal, so the first type of decimal, also known as repeating decimal, whenever we find this, also called recurring decimal, such numbers are also rational numbers. Okay, such decimals are also, they have also formed from rational numbers. That means I'm saying that these decimals can be written in the form a upon b. These decimals can also be written in the form a upon b. Let's come to the next one, which is 3 to 1. So there's no specific pattern in all the digits that appear after the decimal point. What do we do then? Well, in such cases, such decimals can't really be written in the form a upon b, and these ones are irrational numbers. Irrational numbers. Okay. Now, a quick way to remember all this is just remember one thing. If your decimal expansion is non-terminating and non-repeating, then you have an irrational number. Non-terminating, non-repeating, only such decimals have formed from irrational numbers. Rest everything is rational. That's it. If you remember this much, you're sorted. Anyway, so this was about the recap of what we had studied. Let's move on to the first section in your textbook. But before that, we want to solve a question. A question which is related to what we studied in class 9, but it has appeared in the board exam once. Not very recently, but in 2019, this did appear in the board exam. Why don't you take 5 minutes, pause this video, take 5 minutes and try to solve this question. Okay, so I hope you have given this a try at least. Let's solve this question. Find how many places of decimal the decimal form of this number will terminate. After how many places? So first we need to find out the decimal form of this number and then see how many places are there, how many digits are there after the decimal point. But it's only of 1 mark, you see. That's too much work for 1 mark. Can I find the answer without actually converting this into decimal form? So I want to find the answer directly without actually converting it into decimal form. To do that, what I'll do is, I'll try to figure out how many zeros are there in the denominator. If we can do that, we'll be able to find the answer. Can you find out how many zeros are there in the denominator? Try expanding just the denominator. Let's see how. 27, okay, let me choose another color. Let's see how. 27 upon 2 cube multiplied by 5 to the power 4 multiplied by 3 squared. Well, how can I get a 10? See, I have 3 prime numbers, 2, 5 and 3. Which 2 prime numbers multiply to form the number 10? 2 and 5, right? So, if you want, you can expand this. So I'm doing this for the sake of understanding. You don't need to follow all these steps. You can just directly write it. So see, 2 into 2 into 2, and then we have 5 into 5 into 5 into 5. This multiplied by 3 square. I'm just going to leave 3 square as it is because it's not going to help me get some zeros in the denominator. Okay, now that we have this, let's multiply this 2 with this 5. Then we'll multiply this 2 with this 5. Then we'll multiply this 2 with this 5. Okay, so I get 10 from here, I get 10 from here, and I get 10 from here. 10 into 10 into 10, that gives me 1000. Okay, 1000 is there. This is left. So now let's see, what do we have? We have 27 in the numerator. In the denominator we have 1000, which is multiplied by 5, which is multiplied by 9. Okay, well, 9 3s are 27. So we have 3 upon 5000. So we've simplified it quite a bit. So looking at this number, there's still some work we need to do on this. We can't say that the decimal terminates after 3 digits just because there are 3 zeros in the denominator. Because there is a 5 also, right? What if 3 is divided by 5? You get 0 point something. So that introduces a decimal number as well. So what we are going to do is, we just want powers of 10 in the denominator. So I'm going to multiply 2 here and 2 in the numerator also. No harm done, right? I can do that. So what I get next is 6 in the numerator and 10,000 in the denominator. Now it's a pretty simple number. You can easily claim that after 4 decimal points, because there are 1, 2, 3, 4 zeros, so after 4 digits, or in other words, this decimal will have 4 digits after the decimal point. Okay. Let's move on to the first section which is mentioned in your textbook, which is about the fundamental theorem of arithmetic. Okay, so this theorem says that every composite number can be expressed as a product of primes, a product of prime numbers. We all know that. We all studied prime factorization of any number, right? So if I give you any number, you can prime factorize it, like it has been done for this number 1080. We've used the factor tree. You can use the division method also, up to you. But if you find the prime factorization of any number that I give you, this theorem says that the prime factorization is unique. For example, the prime factorization of 1080 or 1080 is unique. It's always going to be this. It's always going to be 2 cube multiplied by 3 cube multiplied by 5. Always. No matter who finds, which person finds the prime factorization of 1080. It's always going to come like this, and that's what this theorem is saying. Of course, we are not considering the order. So you can't say that 3 to the power 3 into 2 cube into 5 to the power 1. This is different from this, and hence we don't have a unique factorization of this number. This is not a sound argument, okay? This is not a good argument, because this is actually equal to this. We're not bothered about the order right now. So when we are saying that the factorization is unique, it simply means that no matter which term you write first, if you expand this and you multiply, you're always going to get the same number, right? And that's why this theorem seems a little obvious, but it can help us in so many ways you're going to see. You might have already seen it since you are focused on preparing for the exams. Okay, let's move on and see how we apply this theorem. Where does this theorem help us? So, as per your syllabus, it has many applications, by the way, but you have to study about two major applications. Uh, First is finding the HCF and LCM of two numbers. Uh, and then you have to prove that some number is irrational. Specifically, when proving that root 2 is irrational, this theorem does come into picture. We'll see how. So here's another question. Take a few minutes, try to solve this, come back, and then look at the solution. Okay, this is a very recent question. It just came last year in the board exams. Let's try to solve it. So the ratio of HCF to LCM of two numbers. That's what we have to find. So we have to find out the HCF of the least composite number and the least prime number. So let me write least composite number and least upon the LCM of the same two numbers. Instead of writing this entire thing, now I'm going to just write down what is the least composite number, by the way. If you say 1, I must warn you. See, 1 is neither prime nor composite. Uh, what else? 2. 2 is a prime number, it's not a composite number. 3 is also a prime number. 4. Okay, so 4 it is. So I'm just going to write 4. And what is the least prime number? It's 2. So let me erase all this text in between and write the proper numbers, because we found out what is the least composite number and what is the least prime number. So 4 comma 2. Okay. HCF of 4 comma 2, it's really easy to find out. It's 2. And LCM of 4 comma 2, it's 4. I hope you know how to do that. Okay, you can either use the prime factorization method or the division method or any other method that you know of. So the ratio, you'll have to simplify this a little bit more. 1 upon 2, or you can say 1 is to 2. That's the answer. Okay, this was very easy. That's why it was of 1 mark. Actually, it was a multiple choice question in your question paper, but here I've removed the option so that we can solve from scratch. Okay, let's try this one. This is also a 1 mark question, but it uses something which you have learned in your textbook, which you might have learned in your class. Try this. Let's solve this question now. Okay. The LCM of two numbers is given, and the HCF of those two numbers is also given. It's 13. What are those two numbers? We don't know. Let's call them A and B. Okay, so LCM of A and B is given. HCF, or the highest common factor or the greatest common factor, is given as 13. This is given to us. If one of the numbers is 26, all right, wait. First number is given to me. So A, let's call it A. A is given to me as 26. I don't know B. So it's also given that the first number is 26. We have to find the second number. Now, if you recall, a very nice relationship between the LCM and HCF of two numbers and the numbers itself. I'm going to write that relation. LCM of two numbers, LCM of A and B, when it is multiplied with HCF of A and B, you get A multiplied by B. So LCM of two numbers multiplied by HCF of two numbers is actually equal to the product of those two numbers only. Those two numbers. The product of those two numbers. We'll use this and we'll figure out the answer now. So 182 multiplied by 13 is equal to 26 multiplied by B. Easy to find out. 13 into 2 and then 182 divided by 2, that's 91. That's the value of B. Okay, so B is equal to 91. 1 mark, very easy. Let's try a 2 mark question now. This might be a little complicated, but still, if you have studied this chapter, this would be an easy enough question. It's on the same similar concept. Alright, let's look at the solution now. So two numbers are in the ratio 2:3 and their LCM is 180. What is the HCF of these numbers? If the ratio of two numbers is given, can I say that one of those numbers might be this and the other number might be this? 2x and 3x can be those numbers, right? Okay. So we have some information about the two numbers now. Now if A is this and B is this, can you find their LCM? Think of how we found LCM using prime factorization. Let's write A as 2 into x. Well, we don't necessarily know that x is a prime number, but still this method is going to work. How? I'll show you. Okay, then let's write b as 3 into x. We need not worry about whether x is a prime number or not, because x appears in both these cases. So if we have to find out their LCM, it's going to be 2 into 3 into x, isn't it? Now that we have figured out what is the LCM of 2x and 3x, we also know its value. So you equate it to 180, and from here you get the value of x, 180 upon 6. So you get x as 30. Now that you have x's value, you can get the value of 2x, you can get the value of 3x, and you can find out the HCF. That is one way. The other way is use the relation that we learned. The relation was LCM into HCF is equal to A into B. So 2x into 3x. So LCM is 180, HCF is what I have to find out. 6 times x square. So 6 times 30 into 30. You calculate this, find out the value. That is going to be your HCF. Let's do that quickly. So 180 will get cancelled, and you will have HCF as 30. This is one way to find the HCF of these two numbers. But let's say you've forgotten this relationship between LCM of two numbers and HCF of two numbers. What to do then? That can also be done. Let's see how. So instead, this time what we will do is, we'll figure out the values of A and B. Since I know what X is and I know what A looks like, I know what B looks like, I can find the actual values of A and B. A is equal to 2 into 30 and B is equal to 3 into 30. So 60 and 90. Can you find out the HCF of 60 and 90? You can use the factor tree method, or you can use the prime factorization method, the division method, up to you. You know how to do this. You are in class 10 and you'll get the value as 30. So same answer. Okay, now that we are done with this, let's move on to the next concept. The next part that your textbook covers is irrational numbers. The chapter's name is real numbers. We have covered the rational number part. We are moving on to the irrational numbers now. We did study something about irrational numbers in class 9, if you remember. We at least know how the decimal expansion of irrational numbers are, how we can plot those things on number line and stuff like that. So we have studied these things. In this section, we want to prove some things like this, that root 2 is an irrational number, and the theorem that we studied before this is going to help us. What's that theorem? This one. So let's go step by step. Okay, first let's look at the first theorem. So this theorem says, if p is a prime number and p divides a square, that means p must be dividing a also. So let's try to understand the first theorem in greater detail. A square. A is a number. It may be a composite number, it may be a prime number, but its prime factorization is possible. So let's say A can be written as 2 into 3 into other prime numbers into P. P is also a prime number. So A square will be A into A. That means this thing written two times. So 2 into 3 into and so on till P multiplied by 2 into 3 and so on till P. The theorem is saying if P is dividing this quantity, which is A square, if P is dividing this quantity, that means P must be dividing A also. Can't we see that? Of course, P is dividing A because it appears in the prime factorization of A. So that's what the theorem means, okay? Let's try a question based on this theorem before we move on to the next theorem. So here's the question. If there is a prime number P and K is any positive integer, if P divides K square, then which of the following is definitely divisible by P? You can say for sure that if P divides K square, then which of these, this one, this one, this one, or this one, which of these four quantities will definitely be divisible by P? Okay, I'll quickly tell you the answer. You can pause the video, think through, and then come up with your answer. So here's the solution. See, from theorem 1, we know that P definitely divides K. This we know. So, of course, this is true. It divides K. If it divides K, it will definitely divide 7K. Okay? And if it divides K, it will divide K when it is multiplied to itself 3 times. So it will also divide K cube. Okay. What about K upon 2? If P divides K, will it be able to divide K by 2 also? Think. I'll quickly give you an example. Okay. So 10 and the prime number is 2. So 2 divides 10, but can 2 divide K by 2 also? So that means 10 by 2. Is this possible? I mean, will 2 completely divide 5 without leaving any remainder? No. So not K. Apart from the first one, the all three will definitely be divisible by P. Let's move on to the next theorem. So the next theorem says that it's a statement. It says that root 2 is an irrational number. Uh, we might prove this theorem, but you have this proof in your textbook also. But we'll see. If this question has appeared in the exam, we'll prove it once again. Okay. But for the rest of the chapter, you can take this as an assumption. Okay. You can take this as something which is known. So let's say if someone asks you to prove that 5 root 2 is irrational. Okay. Uh, there are two ways to go by it. You can either start from scratch, assume this to be P by Q and follow the proper process and so on. Or you can quote this theorem. You can say that since the theorem number 2 says that root 2 is an irrational number, we believe that root 2 is an irrational number. If root 2 is an irrational number, any integer multiplied with an irrational number has to be irrational. You'll have to mention the reason properly, okay? Uh, for example, you can't mention that any number multiplied with root 2 will be an irrational number. To give you an example, root 2, when it gets multiplied by itself, you get something rational. Okay, so if you're using this method, you have to be very precise in writing the statement. If you think you can't be that precise, then go by this method. We'll see this method soon. A quick recap of the two theorems we've just studied. Let me clean it up. The first theorem is if p divides a square, then p must be dividing a also. You have to remember here p is a prime number. The second theorem says that root 2 is an irrational number. That's the theorem. Here are a few questions that appeared in the board exam in 2020. There's high probability of appearing in 2024 as well. So try this out, okay? Try this out. Try both of these actually. Try both of these. This is a practice session, so we want to be prepared for our exam. Try both of these questions, all right? Okay, so let's look at the solution now. There are two ways to solve the first question. I'm going to show you both the ways. First, the formal way. The second one is a little bit informal but faster method. So we'll solve the first question. Solution of the first question. Show that this is an irrational number. We're going to prove it by contradiction. We'll assume that 5 plus 2 root 7 is a rational number. That means it can be expressed in the form P upon Q. P upon Q can be cancelled and you might get two numbers. So if there is some common factor between P and Q, you can cancel them out and you get two co-prime numbers A and B. A and B are co-primes. Okay, so 5 plus 2 root 7 is equal to A by B. We're just going to focus on that. So we'll directly assume that 5 plus 2 root 7 is equal to A by B. That means this number is a rational number where A and B are co-primes. Okay. Let's juggle a little bit. So this proof by contradiction works something like this. Uh, if we have to prove that something is an irrational number, we assume the contradictory statement. We assume that it is rational. While doing the calculation and stuff, we encounter a stage, we come to a stage which is contradictory, which says that the assumption that we made must be wrong. And that kind of proves that the given number is irrational. Okay, so let's juggle these numbers and we'll write A upon B minus 5. This is equal to 2 root 7 or okay, let's go step by step. So here we have root 7 as A minus 5B upon B, and this 2 will get multiplied in the denominator. Okay, if this 2 moves to the other side, right, this 2 also moves to the other side, so it goes into the denominator. Now if you look at this, you'll see that A minus 5B upon 2B, A and B are co-primes, but they are integers, right? They are integers. These are integers. So, will the numerator be an integer? What do you think? A minus 5B, will it be an integer? Think in terms of properties of integers. An integer subtracted from 5 multiplied by another integer, it's going to be an integer. Okay, so let's call this integer c, and 2 times b is also an integer, let's call it d. Both are integers. What is this statement telling me? It's telling me that root 7 is rational. That means I must have made an incorrect assumption. What incorrect assumption did I make? The incorrect assumption I made earlier was that this number is rational. That means this number is actually irrational, hence proved. This was the first method. This is the formal method. I advise everyone to write in the exam using this method. Let's look at the second method of solving the first question itself. So, in the second method, we are going to use the properties of rational and irrational numbers. When it is given that root 7 is irrational, what can you say about an integer multiplied with an irrational number? This is also irrational. A non-zero integer, when it gets multiplied with an irrational number, results in an irrational number. You need to write this entire statement in your exam if you want to solve it by this method. Okay, all right, so this is irrational. Let me call this k. Let's just call it k, where k is an irrational number. All right, what do you get when you add an integer to an irrational number? You get an irrational number. So just by using these statements, you will be able to prove that this thing is irrational. Okay, so this is another way. It's kind of an unconventional way, but yeah, if you solve by this, even you have to write the correct statement, the correct reasoning, you will get marks. Let's move on to the second question now. Check whether 12 to the power n can end with the digit 0 for any natural number n. Alright, natural number n. So n cannot be 0. Okay, n itself cannot be 0. We're clear of that. We know that. 12 to the power n, if it ends with a digit 0, that means it must be divisible by 10. Let's say if 12 to the power n ends with 0, then it must be divisible by 10. Right? But 10 is not a prime number, so we'll say this same statement in terms of prime numbers. So we'll say that it must be divisible by 2 as well as 5. Do you agree with this statement? So it must be divisible by 2 as well as 5. Okay, this, if we're clear with this much, then we will be able to understand the solution easily. So 12 to the power n can be written as 12 into 12 into 12 n times. 5 must be a factor of this for 0 to appear in this expansion, right? In other words, whatever we get here, it must get divided by 5. We can see that it is getting divided by 2. So that is there. It's getting divided by 2. But only getting divided by 2 is not sufficient to get a 0. It has to get divided by 2 also, 5 also. It gets divided by 2, we all agree to that. 12 gets divided by 2. But does this number get divided by 5? No. There is no 5 appearing. So if you want to prime factorize this, this is what you're going to get over and over again. And so on. No 5 appearing here. So we've proved that this, or we have shown that this number will not have a 0 at the end, whatever value of n you take. I hope you understand the solution. Okay, let's move on to the next part. This is an interesting question. It's very similar to proving that root 2 is an irrational number. So that's your hint. Take 5 minutes, try this out. Okay, let's look at the solution of this now. Again, we are going to prove this using the method of contradiction. So, if we have to prove that root 5 is an irrational number, we assume that root 5 is a rational number. That means it can be represented in the form a upon b. I hope you will write all the statements, okay? I'm skipping some steps, just want to show you the solution. Okay, so let's assume that root 5 is a rational number and hence it can be written in the form a upon b, where a and b are co-primes, okay? Okay, let's juggle this a little bit. So b root 5 is equal to a. Let's put the square, let's whole square on both the sides. We can do that. This will give me b square into 5. So that's 5b square equal to a square. Okay. This tells me that a square is divisible by 5. This tells how? So b square is equal to a square by 5. So see, if you are dividing a square by 5, you get an integer. That means a square is divisible by 5. Now remember the theorem that we studied, the first theorem under the heading irrational numbers. If 5 can divide a square, 5 is a prime number. So if a prime number can divide square of any number, this means 5 can also divide a. This is what the theorem says. Okay. Now we use this theorem to express a in this form. If 5 can divide a, can I write a as 5 times some other number, some other integer, 5k? Can I write that? Of course, some other positive integer. So a is equal to 5k. We're going to use this here. And we are going to shuffle that once more. So root 5 is equal to a upon b, and this time a will be written as 5 times k, and let's rearrange this. Root 5 is equal to 5k upon b. So b goes to this side, root 5 comes to that side. If you so you can write root 5b is equal to 5k. Again, square both the sides. What you get is 5b square is equal to 25k square. This 5 cancels and comes here. So b square is equal to 5k square. Okay. Something very similar to what happened with a that time. Okay, so we have this. Or b square upon 5 is giving me some integer. This is some integer, right? So can I say that 5 completely divides b square? And if this happens, then we can say that 5 must divide b also. Okay. So 5 divided a also initially, and 5 divides b also. That we have proved here. That means 5 is a common factor between a and b. What did we assume at the start? We assumed that root 5 is equal to a upon b, where a and b are co-primes. While shuffling and juggling with what we had, we find out that 5 is a factor of a also, 5 is a factor of b also. That means our assumption must be wrong. So our assumption that root 5 is a rational number was wrong. If this was wrong, then what is right? The right statement is that root 5 is an irrational number. A very similar way you prove how root 2 is irrational or root 3 is irrational and so on. Alright students, with this we've come to the end of this session, and in this session we've not just seen the previous the questions that appeared from real numbers in previous years in your board exam, but we've also solved the different types of questions that you get in your board exam from that chapter. Okay, so concluding this now, thank you so much for joining. In the next class, we're going to do a one-shot revision, very similar to this one, for chapter number 2 of your NCERT. Thank you so much for joining. Bye-bye. Take care.